It's a great pleasure to be here and to meet many old colleagues and meet new people. And I'm especially honored to have been invited by Yanir and Scott, and especially Scott was a visitor at Harvard when I was a graduate student there. And almost all of my colleagues, by which I mean the other graduate students, were studying number theory or algebraic geometry. And the one thing I learned from them was that the most important thing to study was the moduli space of Riemann surfaces. But the only person whose viewpoint on this topic I could understand was a great complex analyst, namely Scott. And so I've learned a tremendous amount about moduli spaces from Scott, and I still love complex analysis, even though I've drifted into these adjacent fields, which I'll discuss today. Okay, so thank you for having me. So I want to discuss a very basic problem in dynamics, which I'll formulate as the following. What is the simplest, interesting dynamical system? Well, I need to define the words, but there's some other, there's actually a preliminary question about integers, which I want to address first. But before I begin, I want to say that there's a lot of people who have contributed to the story that I'm going to tell, and I won't have time to mention them all or to go into the history, but let me just mention some. Brandhorst, Serge Cantat, Dick Gross, Eko Hironaka, Nagata, Ogisu, and many others. Okay, so here's the warm-up question. What is the smallest integer bigger than 1? Now, before you answer, let me tell you that by integer, I mean algebraic integer. So the roots of a monic polynomial with integer coefficient. And by smallest, I mean the following. When you have an algebraic integer, it shouldn't be thought of as coming along as a single number in the complex plane. You have all the roots of its minimal polynomial, all of its Galois conjugates. And some may lie inside the unit circle, some may lie outside. And a good way to measure the size of an algebraic number is to take the product of the conjugates that are outside the circle. And that will always be a real number because the complex roots will occur in conjugate pairs. And this number is called the molar measure of the integer lambda. Okay, so here's a particularly nice example. This is an algebraic number which is called a Salem number. And it has the beautiful property that it's a positive real number, but its Galois conjugates all lie on the unit circle except for one other. And this one other is the reciprocal of this number. So what's the molar measure of a Salem number? It's just the number itself, because this is the only conjugate that's outside the unit circle. So this is, capriciously chosen degree 10 number. Here's its characteristic polynomial, the approximate value, 1.17628, et cetera. This number was discussed by Lamer already in the 1930s, and it has a special role in this theory. So in fact, if you fix a degree, the set of Salem numbers of a given degree form a discrete set. And so there's a minimum Salem number of each degree. So for example, the minimum Salem number of degree 2, the minimum quadratic integer, is the root of this polynomial. And degree 4, it's this polynomial, and so on. And here's the numerical values. And you can see they start to go down. And then at 10, it becomes quite small. And then they start to sort of oscillate a little bit. But no one has ever seen a number that's smaller than lambda 10. So the answer to my question, what's the smallest algebraic integer, is actually unknown. But there's a guess for what the answer is, which was formulated by Lamer, that this number I've just shown you, lambda 10, has the smallest molar measure over all algebraic integers. Or an easier open problem to keep in mind is Lamer's number is conjectured to be the smallest Salem number. Okay, now this raises another question, which is what is Lamar's number really? So Lamer found this number. This is one of the, using computers, it was one of the earliest applications of computers to this kind of search. But we now know a much more geometric way of looking at Lamar's number, and it's the following. So this is an example of a Coxeter diagram. It's just a graph. It's a way of describing a certain quadratic form. So you have a basis for a vector space. There's a basis element for each red dot. And then to describe the quadratic form, you have to know what the inner product is between these basis vectors. And if there's no edge joining them, the inner product is 0. If there is an edge joining them, the inner product is -1. And I should say the inner product of each number with itself is 2. So you get a matrix with a symmetric matrix. This is a convenient way to describe a symmetric matrix with entries 2, -1, and 0. And if I were to get rid of 2 of these dots, this would be the famous E8 Coxeter diagram. It describes the densest packing of spheres in 8 dimensions. Now, whenever you have one of these diagrams, it turns out each dot gives you a reflection with respect to the quadratic form. So an isometry of the quadratic form that preserves the lattice spanned by the basis vectors. And consequently, if we take the product of all of those reflections and take its characteristic polynomial, we get a polynomial with integer coefficients, in fact, a monic polynomial. And Lamar's number turns out to be, for this particular diagram, the leading eigenvalue of that product. Now you might object, oh, maybe the product depends on the order in which you take the product of these 10 reflections, and of course it does, but only up to conjugacy. So this characteristic polynomial is uniquely encoded by this diagram. And so this is a easy to carry around a geometric description of what Lamar's polynomial is. It's the characteristic polynomial of what's called the Coxeter element for the E10 Coxeter diagram. And in fact, inspired by some work of Eko Hironaka, I investigated the general theory of Coxeter groups, and I proved that in that limited regime, Lamar's conjecture is true. That is, if you look at Coxeter groups and the automorphisms of lattices that arise from these groups, you get a certain set of algebraic integers, and of those, the one with the smallest molar measure is, in fact, Lamar's number. I told this to Jean-Pierre Serre, and he said, oh, you must have been very disappointed. Because of, it would have been even better to discover a counterexample to Lamar's conjecture. So anyway, so this is one of the settings where we know Lamar's conjecture is true and where we kind of know what Lamar's number is. So this is an open problem, and I'll mention several open problems as we go through this talk. Okay, now let's turn to dynamics. So dynamics has its origins in, of course, there's earlier work before Poincare, but in Poincaré's work on the 3-body problem. The 3-body problem was to solve the differential equation describing the motion of 3 planetary bodies in the same way that Newton's theorem about ellipses describes the orbits of 2 bodies, in particular good approximation to planetary orbits. Well, there is no solution to the 3-body problem. I mean, there's no closed form for a good solution. And what Poincaré initiated was the qualitative study of the theory of dynamical systems, such as the 3-body problem. Now, the 3-body problem takes place, you can think of it mathematically as the positions and velocities of all the planets right now, and then there's a flow that describes how those positions and velocities changes. So it's a flow on a high-dimensional space. To simplify matters, one thing Poincaré proposes, we take a cross-section of that space. We take a picture of the planetary positions today, and then we predict from that, which we can using classical mechanics, where we'll be a year from now. And then we can iterate that map, and we get long-range predictions for the motion of the planets. So I'm going to work with that idea that rather than studying flows, which are arguably more natural from the point of view of physics, I'm going to study dynamical systems as maps. And within that regime, I'm going to ask, what's the simplest interesting dynamical system? So my dynamical system will be a map from a space to itself. In classical mechanics, this space has coordinates like position and momentum. Mathematically, we'll describe that as just a manifold. To try to simplify life, I'm going to assume that that manifold is compact. I'm going to assume the map is a diffeomorphism. That's meant to accord with the fact that planetary motion is supposed to be essentially frictionless. So you can reverse the motion, which means the dynamical system should be invertible in time. And now I'm going to capriciously require that X is a complex manifold and that my mapping F is holomorphic. Now, why do I require that? It's because I'm a mathematician and I want to add in hypotheses that will make this, this collection of transformations as simple to analyze as possible. So for example, why would you want to work with a complex manifold? You want, this map might have periodic points, and the periodic points are like zeros of polynomials. And you want all the zeros to be there. So by working with complex manifolds, you're kind of seeing a fully enriched dynamical system. Although we might want to also look at the dynamics over the reals of something that starts out with a complex description. Okay, so that's my idea of what a dynamical system is. And now what does simplest mean? And then finally, what does interesting mean? So here's a way to describe the complexity of a dynamical system. It's the notion of entropy. So let me first talk about the English language. So when you're typing on your phone, or when ChatGPT is doing its work, once you've typed a few characters, your phone knows what the rest is that you're going to type. And if you mistype a character, it knows how to correct it. And that's because we're not taking advantage of all of the possibilities of consecutive letters in our language. We're not randomly writing A, Z, Q, L, P space, but there's only a certain number of possible patterns of length n that are valid English sentences. And you could ask, oh, well, how many valid English sentences are there that are 100 characters long, or English paragraphs, or English books? And it turns out, according to the cryptographers, that the answer is there's about 3 to the n possible English books that have n characters in them. So we're barely using a bit, a single binary bit, each time we write a letter. That's good. That allows us to error correct our communications. So that's the idea of entropy. It counts the growth rate of patterns subject to some constraint. So here's what I just said in terms of books. It's just 3 to the n, not 26 to the n. And what's the entropy of one of my dynamical systems? Well, it's almost the same. What we do is we have a compact space X, and we take this space and we cut it up into some regions, which we might label A, B, and C. And now when we have a point in this space, we look at its orbit. We start iterating the map, and it moves through our space, landing in these regions with different labels. And so associated to an orbit, there's a string of letters, in this case, A, B, B, C, B, A. And if I take a different point, I'll get a potentially different sequence of letters. And so once I've subdivided the space, I can relate the dynamics to sort of a language. The dynamics determines the language. And I can ask, what's the entropy of that language? What's the growth rate of the patterns that can arise? And that's essentially the definition of the entropy of a dynamical system. The only problem is there might be something very interesting going on inside of this block A. And so we should take the limit under finer and finer subdivisions of the space. But aside from that, entropy just measures the growth rate of topological patterns of orbits. we might ask ourselves, what is the simplest dynamical system in the sense of what is the dynamical system of minimum entropy? Now, there's certain dynamical systems which have entropy 0. For example, the identity map. But in fact, if you have an isometry of a space, like a rotation of a circle, this also has entropy 0. Once you've seen where the first 100 iterates of a point under a rotation, you can easily predict the next 100 iterates, because you can almost see the rotation number just from the combinatorics of the first 100 points. So what I'm going to study then in my search for interesting dynamical systems is the possible values for entropy on complex surfaces. That is, complex manifolds of dimension 2. Now, you might say, wait, I thought you loved complex variables. Why did you skip dimension 1? And the reason is that for compact Riemann surfaces, there's no interesting dynamics. So let's think about that a little bit. If the Riemann surface has genus 0, if it's the Riemann sphere, all automorphisms are Mobius transformations. They're given by 2 by 2 matrices. They're essentially linear. And it turns out they all have entropy 0. The same thing is true on a torus in the case of genus 1. And for higher genus, it turns out all automorphisms have finite order. So in fact, all the automorphisms have 0 entropy if we're just working on Riemann surfaces. We have to go to 2 complex dimensions before we can really see some interesting complexity in our dynamics. Now you might say, haven't there been, what about the Mandelbrot set and 100 years of work on that kind of thing? That's in one complex variable, but that's not of automorphisms, that's of endomorphisms. It's like the map z goes to z squared plus c. And this is a 2-to-1 map. And to more closely mimic classical mechanics and dynamics a la Poincare, I'm sticking with injective maps, with automorphisms of complex manifolds. Okay, so let's suppose we have a compact complex manifold, the dimension is 2, we have a holomorphic map. We can ask what small values can the entropy assume? Small positive values will be the interesting ones. And here's what's known. If the manifold satisfies a special condition, in particular if it's projective and more generally if it's Kähler, then Gromov and Yamden proved the entropy is recorded by linear algebra. That is, you have this map on a space, but if you want to know its entropy, it suffices to know how the map acts on the cohomology of your surface, say with complex coefficients. And this is just the action on a finite dimensional vector space. That map has a spectral radius, or largest eigenvalue. And these 2 authors prove that the entropy is simply the log of that leading eigenvalue. And that leading eigenvalue, by the way, is always an algebraic integer because the integral structure of the cohomology, the integral cohomology, is preserved by the action of f. Now, I just want to say a word about this proof because I find this statement and the proof is kind of miraculous. So you can think of the map of this complex manifold to itself as being described by its graph. The graph sits in the product of x with x. Now, the graph is a submanifold of this product of 2 Kähler manifolds. And what's beautiful about Kähler geometry is every submanifold is a minimal submanifold. So it minimizes volume within its homology class. So it's a minimal surface. The graph of f is a minimal surface or minimal subvariety. And the incredible thing is when you compose f with itself, so the graph becomes more and more complicated, it's always a minimal submanifold. And what's really happening here is the fact that the graph is so relaxed, it's as tight as possible as you iterate, means that this is the smallest possible entropy for any map in this homotopy class. So holomorphic maps minimize entropy, and that's one of the reasons they're especially beautiful. And then the entropy is always the log of an algebraic integer. And in fact, for surfaces, it turns out that the entropy is always the log of a Salem number. That's an easy consequence of the fact that on the group generated by curves on a surface, the intersection pairing has signature 1n. So in fact, we're driven into the world of Salem numbers simply by trying to study entropies on complex surfaces. I should say there are non-Kähler surfaces, but we can exclude them because all their automorphisms have entropy 0. Now, in fact, there's a complete classification of the surfaces that admit interesting dynamics. This was carried out by Cantat in his thesis, and there's only 3 examples. And 2 of them are very familiar to us. So one of them is the manifold could be a complex torus. That's a generalization of a one-dimensional torus, C2 modulo a lattice. And by the way, again, the automorphisms of these are kind of boring. And then there's something you do not see in dimension 1. There's no analog of these so-called K3 surfaces in dimension 1. And these behave a lot like complex tori, but they're simply connected. And this turns out to be one of the richest sources of interesting dynamics. And finally, it's possible that X is the projective plane. Well, this is not quite true, or rather, it's true up to this word I snuck in here. X is birational to the projective plane. You might say, well, isn't it true that the automorphism group of the projective plane it's like the linear automorphisms of the underlying vector space? And that's absolutely true. But you can obtain more interesting surfaces by blowing up points on the projective plane, something you can't do on P1. And those will, in fact, produce other examples, also very interesting and with positive entropy. And for the experts, there's also something called an Enrique surface. Well, it can be slipped in. It doesn't add anything new to the examples coming from K3 surfaces. Okay, so now I want to combine this result with the result I just mentioned to try to do the following. Somebody is going to give me a Salem number, and I'm going to try to construct from this algebraic integer a complex manifold and an endomorphism of it that has that as its entropy. Now, because that algebraic number, that Salem number, comes from the action on cohomology, the degree of this number over Q is controlled by the rank of the cohomology of the underlying manifold. So it turns out that on a complex torus, you can only get Salem numbers of degree up to 6. On a K3 surface, only up to 22. But on P2, you can blow up infinitely many points. So you can get infinitely infinitely high degree Salem numbers in the case of rational surfaces. So what I'd like to do to survey what's known about the answer to this problem is look at each of these 3 cases in turn and see if we can find automorphisms that are as simple as possible, meaning they have the smallest possible entropy. Okay, so the case of complex tori, that is the quotient of C2 by a lattice, is, as I mentioned, the dynamics is pretty boring, but it can have positive entropy, and it's known by work of Reschke exactly what the answer is, what entropies can be realized, and it's what you would expect. So there is a 2-dimensional complex torus with entropy log of the smallest Salem number of degree less than or equal to 6, which actually has degree 6. But interestingly, complex tori in 2 dimensions don't have to be projective, and this is not a projective manifold. If we wanted to have a projective variety, it turns out the biggest degree would be 4, and we can get down to log lambda 4, not better. So the best possible results, in fact, are achieved in the case of a complex torus, but we don't see Lamer's number because we can't get beyond degree 6 in this regime. And in any case, the dynamics is not so interesting because it's essentially linear. However, it turns out that it's not hard to carry out the synthesis process, because once you have this algebraic number, you can use it to build a rank 4 lattice contained in C2 that somehow is transformed into itself correctly by some linear, complex linear automorphism, and then the quotient of C2 by this lattice gives X. So, you know, the comic book version is number theory has to do with lattices, so do complex tori. Therefore, we can go from an algebraic number to a complex torus without much effort. Okay, now what about rational surfaces? So first, by a rational surface, I mean the blowup of P2 at endpoints. So at end distinct points in the projective plane, you replace each point by the space of directions at that point, or by the space of lines passing through that point. And that adds a new curve, a new P1, to your complex surface. The surface remains smooth when you blow up. And if you blow up endpoints, the second cohomology, which started out being just Z, becomes a lattice of rank n plus 1. And it has the obvious intersection form of signature n plus 1. It's not positive definite. Rather, the intersection form is 1, the intersection of a line with itself on P2. The self-intersection number is 1. And then when you blow up points, these gives what are called exceptional curves. So you get a quadratic form. It's sort of the standard Minkowski form. It looks like the Lorentzian form, only it's over the integers. And so we might think that when studying dynamics on rational surfaces, we should concentrate on this Lorentzian lattice. But it turns out that on any complex manifold, there's a natural canonical class, which is in H2, in the case of a surface, it's a cohomology class which has to be fixed, left invariant by any automorphism. And therefore, there's some vector in this lattice which we can't change. But this lattice has an inner product on it. So any complex automorphism must fix this vector, so it must fix its orthogonal complement. And what is its orthogonal complement? It turns out that that is the EN lattice, the lattice for a Coxeter diagram like the E10 one, which I showed you earlier. So already, as we start to look at rational surfaces, we see hints of Lamer's number emerging. So the canonical class, by the way, has this very simple form. It's this vector -3, 1, 1, 1, 1, 1, with respect to the basis I just mentioned here. And the intersection form restricted to En is one of these Coxeter diagrams. And Nagata showed that not only do the automorphisms preserve this lattice, but they must lie in the Weyl group generated by reflections. So remember, each dot here gives you an automorphism of the lattice. That's sometimes of infinite index in the space of all linear automorphisms of the lattice, or integral linear automorphisms. And the automorphisms of X are not just arbitrary maps preserving this form, but they have to lie in this Weyl group generated by reflections. Okay, so here is one of the synthesis theorems for P2. This theorem is sufficient to answer our question of what is the minimum possible entropy for rational surfaces. And the theorem is the Coxeter automorphism, the one I mentioned before, reflection in all of these red dots, of the En diagram can be realized by an automorphism of a suitable blowup of P2 at endpoints. And as a corollary, if we were to take the E10 diagram, we could get an example that has to do with Lamer's number. But before we get there, let me start by reminding you that these En diagrams for n less than or equal to 8, you've probably seen them in the classification of Lie groups and so on, Dynkin diagrams. These so-called spherical diagrams, which arise when we blow up less than 8 or fewer points, they give you a positive definite inner product on this lattice. And so any automorphism that preserves a positive definite form must be like a rotation. In particular, it's periodic. So we don't actually see positive entropy when we blow up 8 or fewer points. And there's some neat examples, of which I'll just write down one. If you take the map xy goes to y over x, think of that as a birational map of the projective plane to itself. If you iterate it 6 times, you come back to where you started. And that's an instance of this principle, and it can be understood vividly by blowing up, but in the interest of time, I won't elaborate that example. Rather, I'd like to concentrate on this example. It's only when you reach 10 points that you find examples of positive entropy. And in the first case where the entropy is positive, that is when we have 10 points, the map we're realizing has as its entropy the log of Lamer's number. And in fact, it has minimal entropy among all surface automorphisms. So in some sense, the question is now solved. The minimum possible entropy for a surface is the log of Lamer's number. That's positive because lambda 10 is bigger than 1. And it can actually arise on a surface obtained by blowing up 10 points on the projective plane. Now there's a natural question here, which is which 10 points do you blow up? And that turns out to have an interesting answer, and that's the key to synthesis. That is, somebody hands me Lamer's number, I hand them back a complex manifold constructed from Lamer's number. And the way it works is that what you do is you need to constrain the problem somehow. So you constrain your problem to blowing up endpoints not anywhere in the plane, but you require that they lie on a cuspidal cubic. And for the experts, the reason it's a cubic is they should lie on an anti-canonical curve. And then this automorphism that we'd like to construct of the EM lattice turns out to, if we could construct it, it would leave this curve invariant after blowup, and we would get a map of the Picard group of that curve, or essentially it's Jacobian to itself. And this map would give us a piece of linear algebra data, essentially an automorphism of a 10-dimensional vector space. And what we want to do is choose this automorphism so that this map becomes Lamer's map, in which case it leaves invariant some eigenvector, and that eigenvector tells us the position of the endpoints on the cuspidal cubic. Okay, so in brief, sorry, too brief. There we go. Sorry, a little bit of a lag here. Okay, so in brief, there is a construction, a sort of a linear algebra construction that allows us to start with linear algebra data and produce a specific surface. Now, it's hard for me to draw a picture of a blow-up. Yes? Yeah, excellent question. Okay, so the question was, on P2, there's 2 kinds of things that might be called automorphisms. One is you have a holomorphic map of this complex manifold to itself defined everywhere. But the other is you might have a birational map, like this map here, where I divided by x. That map's not very well defined near the origin, because you get 0 over 0 when both x and y vanish. But you might ask, okay, so that's not really an automorphism of P2, but is it an automorphism of a blowup of P2? And the answer to this question is, can I always go from birational to automorphism? The answer is resoundingly no, not in general, but all these examples are very carefully arranged, so the answer is yes. So the point is that for a typical birational automorphism, one of the bad things that happens is a whole curve might be blown down to a point. Now you've lost the information about where you were on that curve. But maybe as you map forward, that point eventually is blown back up to a line. And when that happens, you can blow up the intervening point and get an automorphism. And that's the idea of this construction. So for carefully chosen points on a cubic, you get this dynamical system. And so I've drawn an example of, I've drawn the real points of this iteration on this complex 4 manifold. I've actually drawn their projections to the projective plane. But it turns out the whole thing from the point of view of simulation on a computer is very simple. And this was discovered by Bedford and Kim earlier than my construction. Namely, if you choose A and B just right, you can take this order 6 map and just compose with a translation and get a map on P2 that is the shadow of an automorphism of a rational surface. And in fact, if you choose A, B exactly right, it will be the shadow of a map with entropy Lamer's number. But what I really want to convey is, here's a picture of the dynamics. I've kind of taken a random point and started iterating it. And you can see that there's some sort of strange attractor here. The points are trying to converge to some sort of bizarre locus here, but also that you see a lot of scattering of the points. And that's an indication that the map is very unstable. In other words, if we know the first few iterates of a point, it's still hard to determine their future. And that's a way to visualize the positive entropy that underlies this example. Yes. Okay, so these lines are supposed to be black. These are the 3 coordinate axes, x, y, and the line at infinity. So see, I've written it in this form. So the coordinate axes have an intrinsic meaning. Here is my cuspidal cubic. That's the cusp right there. And then here's another branch over the rails of the same cubic. And here's another branch over the rails. And then if you look very closely, you'll see some dots. There's a blue dot there, and a blue dot there, and a blue dot there. That's 3. 3 more up there, 3 more down there, and then 1 close to the cusp. And those are the 10 points that need to be blown up. So I've tried to pack a lot of information into this picture. Here's a more elaborate picture with those details removed. This is a picture of what happens when you have 11 points. You can carry out this construction for any number of points and get very rich examples of automorphisms of rational surfaces. I should say that when I first started studying this theory, I was certain that automorphisms of rational surfaces were trivial. And so it was a deep part of my own psychological education to realize that how rich and interesting these examples can be. And one of their many interesting features is that these mappings there's an underlying volume form on the rational surface, or an underlying volume form on P2 that's singular along the cubic, and this volume form is not preserved by the dynamics. So we don't have things like Poincare recurrence. These are not really good models of celestial dynamics. What happens is that volume form is expanded when you iterate in one direction, it's contracted when you iterate in the other direction. So for example, in this picture, when you iterate, almost everything converges to this red point right here. It's one of the rare cases where we have automorphisms of complex surfaces, but we can actually predict what happens to almost every point. Okay, so to get closer to physical reality, I want to conclude this discussion by looking at K3 surfaces. So first, the definition of a K3 surface is that it's simply connected and its canonical bundle is trivial. What this means is it's like a complex torus. It has a nowhere vanishing holomorphic 2-0 form. And that in turn means that every automorphism is volume preserving. And volume preserving really forces the dynamics to be complicated and more interesting, perhaps more interesting than for rational surfaces. So if we're competing to see what's the most simplest interesting dynamical system, these might be more interesting. You can't have an attractor, because if you had a ball that maps strictly inside itself, this is a one-to-one map, so the volume would have to be decreased. And we see the richness of this dynamics already when we look over the real numbers. So here's a very specific family of K3 surfaces that Barry Mazur explained to me. They're given by this equation in 3 variables. It looks like this equation has high degree 6. But what's critical is it's of a degree 2 in each variable individually. For example, in x, it's a quadratic equation if we think of the remaining variables as being constant. And what that means is that if I want to find a point on this surface and I'm already given an xyz that satisfies this equation, well, there's a quadratic equation in x which says I'm on this surface. I've already found one root of that equation, so I can change my value of x to the other root of that equation. In other words, there's a 2-to-1 map of this surface to the plane spanned by the y and z coordinates, and I can do the sheet interchange on that map to get an interesting involution. And similarly for the other two variables, y and z. And the way you get a rich and interesting dynamical system is you compose those three involutions. So this is something very concrete in terms of algebra and very concrete in terms of dynamics. It's readily verified that this is an automorphism, and we can easily simulate the dynamics, at least over the real numbers. Now, yes. Sorry?
Is A arbitrary?
Yeah, A can be any real number here. And what we're going to do is we're going to slightly vary the value of A, and we're going to see some different phenomena arising. Other questions? Okay, so one nice thing about this, as Bill pointed out, is that this is actually a family of K3 surfaces, and that's even richer. The rational surfaces I just mentioned were rather rigid. Only in a very specific set of points can be blown up. Okay, so let's look at the dynamics of this surface over the reals to see if that's interesting. So I started cautiously with A, a rather small number. Here's a old Mathematica rendering of what the surface looks like in three variables. It's the real points are sort of like an egg. And remember, you're going down, over, and across, parallel to the three coordinate axes. That's the dynamics. And what we see when we iterate is the following. There are many orbits that just seem to go around densely on a circle. And in fact, the existence of these orbits is not just a numerical accident. There really are invariant islands for the action of this map. What's happening is there's a fixed point in the center of this circle, and the derivative of that fixed point is conjugate to a rotation as a map of R2 to itself. And a deep theorem, the KAM theorem, guarantees that once the derivative is like a rotation, then nearby the map will actually behave like a rotation. It will have lots of invariant circles. And so in particular, this mapping cannot possibly be very rich. It cannot be ergodic, for example. If you start with a point in one of these islands, it can never leave the island. The island is sent to itself. Now, let's just investigate another parameter here. These invariant disks are called elliptic islands in the theory of area-preserving maps on surfaces. Now, when I increase A to 2.5, what do you see? The islands are still there, although they're breaking up into sort of atolls. There's these island chains surrounding the main island. But most importantly, there's this black sea emerging between the islands. This is what the experts call the stochastic sea. And one believes, i.e. physicists are sure, that this locus has positive area and that the dynamics on this locus is ergodic. So in fact, we see an intermingling of almost periodic behavior and the failure of the existence of a dense orbit and this interesting, possibly very complicated dynamics. Now here, I've increased A all the way to 8. The surface kind of looks like a jack at this point. And this is a picture of the surface from above, and I've drawn exactly one orbit. Yeah. Yeah.
The boundary between this periodic area and the ergodic is known, or just numerical?
This is all numerical. So the existence of this stochastic sea at all is something. There's a renormalization argument that predicts it, but I have no proof that it's actually there.
Each island is one orbit?
So the more complicated island chains are periodic orbits. Yeah. So there's fixed points here, 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 and here, and then there's maybe a cycle of order 5.
And
so what I've drawn is actually a couple of orbits, but the closure of each orbit that I picked there is presumably the same. Yeah. Okay, so somehow when I picked the random value 8, I saw a completely different kind of picture, qualitatively different. I couldn't find any elliptic islands. And I only drew one orbit, and the orbit appears to be dense on the K3 surface. Not only is it dense, but look at how nicely shaded it is. It's kind of dark near here, and then there's kind of a little bit of a glow in each of the 4 arms. Well, that shading reflects the invariant volume element on the surface. So not only is this single orbit appear to be dense, but it appears to be uniformly distributed with respect to the invariant volume measure. Okay, so we see as we change the parameters, we pass from almost periodic behavior to a mixture, and then finally to something that might have dense orbits and might even be ergodic. But there's no proof of that. To elaborate this example a little more, let me first go back to this allegedly tame example and blow up the center of the picture. And you see, there's actually a very narrow stochastic C in the middle of this picture. So one could hypothesize that in this family, there is always a set of positive measure, invariant under the mapping, on which the dynamics is ergodic. And one could make up 10 similar conjectures, and they're all almost certainly true, and no one can prove any of them. And let me show you a little bit more about what one might hypothesize. Let's vary this parameter A continuously. Sorry? It depends. I didn't have a stochastic C on the rational surfaces. So you can have a nowhere dense set which still supports positive entropy. Entropy this is topological entropy, not measure theoretic. So it's not required. But it's very likely, as you say, that if there were no stochastic C, that already starts to feel wrong. It seems to contradict positive entropy. Okay, so let me show what happens in a family of these surfaces. We start with this very tame-looking surface, and we're going to slowly deform until we get to the one that appears to be ergodic. So the islands are still there, and then they seem to wink away, and then, oh, they come back, and they reemerge, and then we see something that's mostly islands. Okay, so I leave it up to you to formulate 5 conjectures that are obvious from this picture. For example, it appears that there's an open dense set of parameters where there exist elliptic islands. It appears that there's a positive measure set of parameters where maybe there's a dense orbit, or certainly a positive measure set where there's a stochastic C, or maybe there's always a stochastic C, or maybe there's always an elliptic island. It's just too small for me to find when A is equal to 8. All of these conjectures are open, and the truth is, it's not going to help you that this is a family of K3 surfaces. The picture we're seeing here is characteristic of all families of area-preserving maps on surfaces. And there's a yet to be justified renormalization theory that says that all families should essentially behave in the same way. Okay, so that's one reason why I like this example and think it's very rich. But remember, I'm a complex analyst. And so when I saw these islands, I was tempted to perform the following experiment. This failure of the existence of a dense orbit, it might be due to my insistence on reality. That is, if I go in the imaginary direction, take one of these points that's trapped in one of these islands and push it just a little bit into the complex direction, maybe then it will be allowed to escape the island and it will go everywhere. And well, here's what the result of that experiment. So I just took one point here, I pushed it up a little, I looked at its orbit in the complex, and then I projected back to these real coordinates. And this is what the orbit looks like. So again, it appears to be dense. I mean, it's in a 4-dimensional space. So this is fairly weak evidence that it's dense. But it's not completely implausible because as you can see, again, there's sort of a density here that the orbit appears to be uniformly distributed with respect to, and that density is the one predicted by the invariant volume element, now not on the real locus, but in the complex domain. Okay. So motivated by that question, by this observation, I began to wonder if there could be islands in the case of complex K3 surfaces, just like there are islands over the rails. Maybe there's an island up here, so to speak, in the extra dimensions. Maybe there's even a disk that's mapped to itself. Maybe it's even mapped to itself by sort of an irrational rotation. Those things are known to exist in other complex dynamical systems. They're called Siegel disks. And so despite the evidence provided by this picture, one of the first things I investigated in this area was whether or not complex islands can exist, and the answer is they can. So in fact, there is a complex K3 automorphism with positive entropy that has an invariant disk. These are called Siegel disks. So there are islands over the complex numbers. Now the next thing I should do is show you what that island looks like. And also this map has no dense orbit, but and by the way I built this map was using a degree 22 Salem number, and as a consequence, the surface in question is not projective. So I don't know how to draw a picture of this surface at all. It's like one of these complex tori that doesn't have any meromorphic functions on it, only it's much worse because I don't even have something like a lattice available to show you for this example. Sorry? It's still Kähler. So all K3 surfaces are Kähler, famous theorem of my colleague Yum-Tong Su. Oh, okay, so complex islands do exist, but you have to really work to find them. So, well, we'll get to that in a moment. First, I want to point out that one can think of this fact that this example was not Kähler as a positive rather than a negative. So there was a famous conjecture of Kodaira, which said that if you have a compact Kähler manifold, then you can deform this manifold. You can continuously change its complex structure until it becomes a projective variety. And Voisin and Ogisu have provided counterexamples to this conjecture. And in particular, Ogisu showed that if we take this bizarre 4-dimensional example, this bizarre surface with the Siegel disk, we take the graph of the automorphism, think of that as lying in the product, and we blow it up, then we get a simply connected 4-dimensional manifold, and it's a counterexample to this conjecture of Kodaira. So for those interested in non-projective manifolds, there's something to be exploited and studied regarding this slightly bizarre example. This example, the surface has no curves on it whatsoever. So it's kind of invisible. But on the positive side, I'm willing to formulate the following conjecture, that on a projective K3 surface, this can't happen. And every time I've tried to find an actual complex example where I have a positive entropy, I seem to have a dense orbit. Now, as I say, it's quite hard to even do a robust experiment proving density of an orbit on a 4-dimensional manifold. But this is one of the many absolutely fundamental conjectures that's open in this field. Okay, yes?
So you formulated this conjecture based on a futile search?
Exactly. Exactly. So there's slightly more. There is a heuristic argument. So in the case where I could find a Siegel disk, what was essential was that we have a fixed point for the mapping, and the determinant of the derivative of the map at that point, i.e. the Jacobian determinant, is a irrational number on the circle. It's not a root of unity. It turns out that for projective K3 surfaces, if you have a fixed point, the Jacobian determinant is always a root of unity. And that creates resonances which make it much harder for Ziegeldists to exist. So there's mild heuristic reasoning why such thing, if not existing, will at least be hard to find. Okay, so returning to entropy, this took me about 10 more years. Let me just finish this discussion with the statement. There exists a projective K3 surface which realizes Lamer's number. And this is, as I mentioned before, it's optimal. Actually, we know it's optimal because on K3 surfaces, the Salem numbers that arise can only have degree 22 or less. All the small Salem numbers of degree 22 or less are known, and Lamer's number is certainly the smallest. Okay, so just a very rapid swipe through what we know about this Lamer's automorphism. Here's an elaborate theorem which tells a lot about the numerical invariance and the structure of this, the action on cohomology for this Lamer example, what its characteristic polynomial is, how it acts on H20. And amazingly, Elkies and Brandhurst found an explicit projective model for this surface. They didn't find a model for its automorphism. It was already incredibly arduous to even find a description of this K3 surface explicitly. Okay, so I'm not going to go through this in any detail at all. I'll just say that the idea in all of these things is to start with number theory, our Salem number, use that to construct some lattices, then add some Hodge theory to that picture so that it looks like the Hodge structure on a K3 surface with the required automorphism. It turns out that there's some splitting. The behavior of the characteristic polynomial at some primes is relevant because a cyclotomic factor involving a root of unity will arise. The lattices you get are not unimodular, so you have to use gluing theory to put them together and build the K3 surface. You also have to leave the Kähler cone invariant, which means you have to be able to draw this black line without it crossing any of the red lines. I tried in the degree 22 case, I did that by getting rid of all the red lines. That turned out to be too radical. There's a way to allow some red lines, but not get rid of all of them. And all of these advances in my own understanding of K3 surfaces were required to be developed before it was possible to see this projective example. Okay, and then finally, there's a Torelli theorem, which says if you can construct the example from the perspective of Hodge theory, then it actually exists as a complex manifold. Okay, so I'd like to depart from K3 surfaces with the following neat observation, which is that in mathematics, it's very important to both ask the right question, perhaps more important to ask the right question than to give the right answer. And one question you might ask is, what are the Salem numbers that arise from automorphisms of K3 surfaces? Well, that question turns out to be, I would argue, too hard. And Simon Brandhorst found the right question. And there's a beautiful theorem about which Salem numbers can arise from automorphisms of K3 surfaces. But the theorem uses an idea that I like to call stabilization. So you don't try to answer the absolute hardest form of the question. You allow yourself a little slack. So here's his theorem. If a Salem number has the right degree that it can arise from a K3 surface automorphism, then you can take a power of it and realize that power. And so you might not know all the Salem numbers that arise, but you know all the fields that arise because lambda and these powers will typically generate the same field. Okay, one last picture of a K3 surface and one last remark. Moduli spaces. As I told you, I learned from Scott, David Mumford, and many other people in my early graduate career that what we should really be studying is not K3 surfaces. We should be studying moduli spaces of curves. And there are analogous questions that are relevant to the study of the moduli spaces of curves. And one of the analogous questions is the following. This moduli space of all Riemann surfaces of genus G comes equipped with a natural metric, and we know what the elements of the fundamental group are. They can be described as maps of a surface of genus G to itself up to isotopy, the elements of the so-called mapping class group. And each of these mapping classes has an associated entropy, which is the minimum entropy of a map isotopic to F. This has to do with the theory of pseudo-Anosov mappings that's developed by Thurston and others. And this entropy is essentially the length of the loop on moduli space represented by this element of pi 1. So there's an analogous question that lives on the world of real surfaces, and it's a more topological question. And the question is, what is the length of the shortest loop on moduli space for each genus G? And this is tantamount to, again, finding, so to speak, the simplest automorphism of a surface of genus G. We want to find an automorphism of positive entropy, but where the entropy is small. And in brief, if you, in genus 1, this is tantamount to finding a hyperbolic matrix in SL2Z whose leading eigenvalue is as small as possible. And famously, 2111, whose leading eigenvalue is the square of the golden mean, this gives a map of the torus to itself, which has the minimum possible entropy. And that in fact comes from the Salem number of degree 2. Now, beautifully, these authors, Lano, Tifo, Eko Hironaka, Eiko Kim, Fardlanger, Margalit, etc., showed that one can generalize this discussion to higher genus. And first, one can concretely find the mappings of smallest entropy in small genus, and one can also find specific examples in every genus that show the entropy, in fact, tends to 0 with the genus. And in fact, you're eventually outside of the world of Salem numbers. And there's some precise conjectures about this, which are getting close to being proved, but many of them are open. But what I want to emphasize about this theory is the following. From this matrix, you get a map of a torus to itself. Well, the quotient of the torus by x goes to minus x is a sphere, and there's branch points to that map. So this group SL2Z is essentially the same as the mapping class group of a sphere with 4 marked points. And what that means is that there's a braid associated to this matrix, a braid on 3 stands, and here it is. It's the standard braid you use for braiding hair. You twist this way, and then you twist this way, twist this way, and twist this way. And for good measure, what we do is we turn this into a link in S3 by first putting a clasp around the braid so it doesn't come untangled, and then joining each strand here to the strand at the top. And what that does is it gives us a 3-manifold that's canonically attached to this matrix, which is itself naturally attached to the golden mean square. And now here's the beautiful discussion I want to end with. This 3-manifold, because there's 2 links here, it fibers over the circle in many different ways. The construction I just gave presents it as a fibration with fibers of genus 1, but because it has higher first Betti number, there are many different fibrations. And the entropies of these fibrations are encoded by something called the Teichmuller polynomial. And the way it works is you put down 3 numbers in a square grid, and then you project along a certain axis and you see a polynomial. So when you project straight down, you just add up the columns and you get the polynomial x squared minus 3x plus 1. But if you project at a slightly skew angle, you get this polynomial, which depends on the angle. It's the integer n intervenes here. And it turns out that Lamer's number arises naturally from this hyperbolic braid. And in particular, there's a map on a surface of genus 5, which is given by doing Dane twists on all the red curves and then Dane twists on all the blue curves. Notice that this looks like the E10 diagram. Its minimum entropy is Lamer's number. And this arises naturally already from this absolutely fundamental braid, which itself arises from the 2111 matrix. So in summary, if you know what the golden mean is, you know what this matrix is, and then you know what this braid is, but this braid knows what Lamar's number is. And so Lamar's number is implicit in the golden mean. That's what this topological construction shows. And this idea of looking at all the algebraic numbers that are implicit in a given one is one of the main themes now in this investigation of short loops on moduli space. Okay, thank you.
Right, so then let me say Kurt will give a lecture tomorrow also, and certainly he's here after the lecture if those who'd like to chat individually. All right.
You have a question?
Yeah.
How much of that work relied on computers?
Okay, so the question was, how much of the work relied on computers? So I'll say all of it. So the reason it all relies on computers is even though there's a lot of conceptual mathematics in there, is that at the end of the day, you need to know, for example, some basic things like simply the fact that Lamar's number itself is the smallest Salem number of degree 10. There is no known conceptual proof of that fact. And no one's going to bother finding one at this point because you can rapidly verify on a computer and rigorously verify that it's true, but we don't know a good reason for it to be true. So because of the fact that to assert that we found minimum entropy requires that we at least know that Lamar's number is the smallest Salem number of degree 10. I should say that there's much more elaborate reliance on computers as well. So all of this construction behind the projective K3 surface, the only reason I believe that construction is correct is because I actually computed the matrices and the Hodge structure explicitly in Mathematica. And I developed a whole package to do this and do infinitely many other examples in principle. And it's only because of that package that I have confidence that the construction is correct. And of course, all the pictures were drawn by computer.
What about higher dimensional, Brian?
Yes, yeah, the great question. Thank you. You are not a plant, right? I was going to turn up, I think you can see. So here's a beautiful fact, which is that let's forget about the complex numbers. Let's take Rn mod Zn and take an element, an n by n matrix with integral coefficients. Then that determines a map of this torus to itself because these integral matrices preserve the integral lattice. And this map has an entropy. So the conjecture so Lamar's conjecture is equivalent to the conjecture that the entropy of T is equal to 0 or H of T is greater than or equal to log lambda 10. So in fact, if you could understand higher dimensional dynamics just on the ordinary real torus completely enough, then you would be able to prove Lamar's conjecture. They're in fact the same question. And this might look appealing at first, and then you remember that if you have a polynomial, you have a characteristic matrix, and that matrix has as its leading eigenvalue the largest root of the polynomial. And so that's how you pass between the torus and algebraic numbers.
Further questions? If not, let's thank the speaker again.